Hello everyone, welcome back to week 2, lecture 3. Today we'll talk about fracture mechanics. In this lecture, we will cover two major topics. What is fracture mechanics and why we need to learn? Secondly, we'll discuss the basic concept and some terminology of fracture mechanics. First, I would like to discuss a concept. What is the difference between fracture and failure? Now we have four options. Answer A, failure is fracture. Those two terms are interchangeable. Answer B, when a material fracture, it definitely fails. C, when material fail, it definitely fracture. D, there are no relationship between those two terms. Which one is the correct answer? The correct answer is B, as boy. When a material fracture, it definitely fails. So fracture by definition means break into several pieces. Failure, it means material lose the functionality. For instance, we can use a stop sign as example. So if I have a stop sign, it's supposed to be stand up and straight and to give a signal. However, if there is a major storm, the stop sign could bend it. You could see scene like this. Or even get worst case scenario. So it could be like that, stop. So therefore, the stop sign will lose its functionality as a stop sign. But the material still stay in one piece. So in this case, we call it failure. It's not fracture. So if in the event of the stop sign break into a couple pieces, so that's what we call fracture. That's the first concept I would like you to be clearly about it. Fracture is not failure. Those are not interchangeable. However, I often hear misconception about it. Now let's discuss what is the fracture mechanics. Fracture mechanics is a discipline that studies materials' mechanical behavior with pre-existing defects. So recall in previous class, we talked about uniaxial tensile stress. We see when material going through a shear stress will develop a shear strain. Let's use the steel as example. We'll develop a linear behavior at beginning, and then material will reach to the yield stress, and then going into plateau, and reach to ultimate stress, and then break. So here it's sigma yield, sigma U, sigma fracture. So in this case, we consider this material is perfect. There is no defects. However, in reality, many material have defect, maybe during the manufacture process or during the service life. One of the obvious examples is concrete. We have many pre-existing defects during the curing process. So therefore, when the material have this pre-existing defects, we have to use a new type of mechanics to study material behavior, which is called fracture mechanics. Fracture mechanics use the solid mechanics to calculate the stress on the crack and study the crack initiation and the crack propagation. So if I have a material and material start to develop a crack. When the material have a crack during the service life, it may not be dangerous. However, when the material crack grow very fast, when this crack propagates very, very fast, that will be the time we have to concern. So again, the size of the crack, the location of the crack, the geometry of the crack, it's very important, obviously. So fracture mechanics is really to characterize the material's resistance to fracture by applying fundamental physics of stress and strain behavior of material, and to understand the crystallographic defects of material to predict the material's microscopic behaviors. There's three major parameters we need to consider. One is crack size and the geometry. This is very intuitively easy to understand. If the crack located in the middle of the material or if in the edge of the material would definitely have a different effect. The same thing with the geometry. How does the crack look like? Does crack have very sharp tip? Those are the important parameters. Stress concentration. How much the stress will concentrate in the crack, and particularly on the tip area. And the last one is the material's intrinsic ability to resist a fracture, which is called the fracture toughness. So why we need to learn fracture mechanics? Because this discipline will help us to answer the following questions, such as how do flaws in the material initiate failure and fracture? For instance, when we manufacture the bolt may have some defects, and how those defects affect the material failure, and how its fracture resistance quantified, and how do different material classes compare. Would a polymer behave the same with glass? And it's also important to understand how do loading rate, loading history, and the temperature affect the failure stress. For instance, when a computer chip going through cyclic thermal loading, how would that, the thermal strain and stress, affect the materials? And also, how do we estimate the stress to fracture? Would the same material behave same, or would a different material behave same? There are several famous quotes I would like to use and to also to help us to understand why we need to learn fracture mechanics. A Professor Callister, the author of the Fundamental of the Material Science, he wrote, I quote, "The failure of engineering material is almost always an undesirable event for several reasons. First, human lives are in jeopardy. We will have economic losses, will interference with products and services." Professor Bazant from Northwestern University, the pioneer expert in understanding concrete mechanics, he said there are three things which typically leads to material or failure of engineering structure. First kind is not follow specification or codes. Second, it's a theory available, but generally ignored. Third kind, which are phenomena unknowing. As humans continue to discover new knowledge, and we often and always have this phenomena unknown. So what is the difference between fracture mechanics with the strength of the material? In lecture 1 and 2, this week we talk about the strength of the material. In that lecture, we discussed how continuous body responded to applied stress. So we consider every material is perfect. There is no defects. There's no voids. So therefore, we use applied stress to determine material strength. As we talk about sigma F, it's your strength F, material at failure strength. Sigma yield equal to S yield. So yield stress equal to the strength of the material at yielding point. Sigma U equal to SU. The stress, ultimate stress equal to ultimate strength of the material. And the sigma F equal to SF. Stress at failure equal to the strength of the material at the failure point. So that's the strength of the material. We're looking at as long as the material strength applied load smaller than the intrinsic material's strength, we're safe. However, in fracture mechanics, we need to consider a pre-existing flaw, which is the most real-life cases. So therefore, there is a third parameter is important. We have to look at applied stress. What is applied loading condition? And then we have to consider what existing flaw and what's a flaw size, what's a flaw geometry, where the flaw located. And then we have to think about it. What is a material toughness? What's a material's intrinsic ability to resist a fracture? Those are the very important concept. So fracture mechanics is a discipline to mathematically study the interdependent relationship between those three parameters. So conventional design approach, it's based on the strengths of the material or structure. So therefore, when I looking at if this is a structure of the material, and when I have applied stress, as long as the applied stress is smaller than yield stress, so then this is a safe design. If applied stress is bigger than yield strain or yield stress of the material, then this is unsafe. We need to go back to redesign. So this is approach. However, this design does not safeguard against the possible failure by fracture. For instance, very brittle material or ductile material go through the ductile to brittle transitional temperature. If it's a lower temperature, ductile material can become very brittle. How about material go through fatigue? How about dynamic loading condition? So as you can see, this is a simplified approach. In real life, we use a fracture mechanics design approach. In this case, we'll consider stress concentration and crack size dependence. So we're looking at applied stress. By using applied stress, we will calculate the fracture parameter, which we'll discuss later in the lecture. And by using that, we'll look at that and compare with material intrinsic fracture toughness. If the fracture parameter smaller than the fracture toughness, this is a safe design. If it's a fracture parameter bigger than fracture toughness, so this is not okay. We will redesign. So as such, it's important to understand the flaw size and the fracture parameters. So again, the evaluation of the fracture parameters are very important. In presence of the visible crack for ductile or fatigue loading condition, fracture mechanics can predict the safety and the life of the structure. So this is a very important concept. And also for non-destructive testing, it's very important to using NDT methods to understand the flaw size, because as we said, a flaw size is very important fracture parameter. So therefore, we want to use a non-destructive testing, and particularly when material structure is still during the service life, to understand the crack flaw size or crack size. And as long as this size is smaller than the threshold, we're still safe. So the material structure still can be in service. So you may have a question. Fracture mechanics does not sound a very old concept, or at least it does not exist in 1,000 years. So why early structure did not fail for ages? For instance, many materials or structures built in the Romans' time, why they're still existing for today. If you look at the early structure with new structures, I put them side to side. On the left, as you can see, most of them, they have arch shape. In this case, the materials only go through compression, if the material have crack, as being clearly shown here, many material has a crack, the crack is not expanding rather than compression, contract. So the size of the crack would not be extended. So there is not many chance for crack to grow or propagates. Number one. Number two, all the design most use arch design. So therefore there is no sharp tips. So therefore there is not any area have a stress will be super concentrated, become a very weak point. In contrast, the newer structure concept of going to up, going horizontal. And as you can see, particularly with current structure steel, and we are building the structures very, very tall and go through a lot of shear stress, tensile stress. So in this case, if I have a defect in the material, so I'm not compressed, I'm extracted. The defects have many chances to be expanded. That's number one, tensile, shear. Number two, as can be seen, there is many complicated geometry which will lead to very sharp tips. In these corners or tips, the stress can be easily concentrated. This will create a very weak spot, or we call it the stress concentration. As a result, the stress can be magnified to order of the magnitudes. That will lead to a very dangerous place for the materials to fail. And another reason is the material's property. There's general two types of material. One, we call it the ductile. Ductile material exhibit substantial plastic deformation with very high energy absorption before fracture. As been showing on the left, this is aluminum. As you can see, when we do a tension stress, as you can see, there is a substantial neck developed by this area. And the fracture surface is not flat, rather than a little cup shape. So here it's kind of like a cup shape, a little concaved. So therefore have a substantial energy absorption. On the other hand, for brittle material, such as carbon steel, if this is a higher concentration of the carbon steel, very strong material, however, it's very brittle. In this case, the material has very little deformation. So if I look at the stress strain curve, recall in the previous lecture, this behavior would be like this. Very high Young's modulus, A lower toughness for ductile material would be like this. You have a lower modulus, a way better toughness. In a real life example, the polymer is very good example of the ductile material, as you can be showing here when we're doing the tensile testing, uniaxial tensile testing. As you can see, substantial deformation developed in the neck area. On the other hand, if you're testing a glass bottle, you will see the bottle will just shatter into many pieces even before any deformation. So as such, the mild steel, high tensile steel, that can be very relative terms. So here are schematic concept to show what's the difference between ductile and brittle material. For very ductile material, we can see the fracture surface become very sharp. The substantial deformation, the substantial shape changed. For less ductile, the original crack will go through some propagation phase, will develop a larger crack. However, for brittle material, we'll have a very clean and a quick snap. So the surface is just like you have used a knife to cut it through. It's very clean surface. To characterize the material property, there's many methods. You could use mathematically to calculate, but humans are very visual. So therefore, it's good to looking at the image. There is one type of characterization methods. It's called a fracturography. So fracturograph is to using a graphic image methods to characterize fracture surface. As showing here, a picture on the left is high density polyethylene going through a significant plastic deformation. This photo is a scanning electron microscope picture has been taken from my research group. As you can see, there's a substantial necking area developed here. This is the original shape, and then the substantial neck area developed in this area. So large deformation. And another photo is developed by CC Technology. And here to show you a tire cord wire loaded in tension. As you can see, again, we have a nice neck area developed in this deformation. As such, this is a ductile material. In contrast, this is aluminum oxide, or people call it a sapphire. Sapphire is very nice, highly crystal material, generally used for semiconductor material. So aluminum oxide or sapphire is a ceramic. It's very brittle material. As you can see here, it's very nice fracture surface. Very clean cut. Clearly is snapped. To summarize what we have discussed in this lecture, couple of take-home message I would like to re-emphasize. First, failure is not fracture. Failure is a material lose functionality. Fracture means material breaking to pieces. Fracture mechanics is a discipline that studies material mechanical behavior with pre-existing defects. It's important to use a solid mechanics to study the stress on the crack and the crack initiation and crack growth. And again, we characterize material resistance to fracture by applying fundamental physics of the stress and strain. And most importantly is we talk about the fracture mechanics design concept is different because we need to look at the crack size geometry, we need to look at the stress concentration, and the stress of a material's ability to resist fracture. It's called fracture toughness. Thank you for your attention for this lecture. Coming next, we'll talk about fracture behavior.